Every measurement in physics is two things stuck together, a number and a unit. Say a distance is just 5 and you have said almost nothing. 5 meters, 5 kilometers, 5 light years. The unit is not decoration. It carries the meaning, and without it the number is noise. This unit is the grammar of physics itself. Where the units come from and how they combine, the deep split between quantities that have direction and those that don't, how to handle the fact that no measurement is ever perfect, and how to sanity check an answer with a rough estimate. Master this, and every later topic rests on solid ground. The whole of physics is built from a tiny set of base units. 6 matter for this course: the meter for length, the kilogram for mass, the second for time, the ampere for current, the Kelvin for temperature, and the mole for amount of substance. Everything else is made by combining these. Every other unit is a derived unit, built by multiplying and dividing the base ones. Speed is meters per second. Force from F equals ma is kilogram meters per second squared, which we name the Newton. This gives a powerful trick, homogeneity. Both sides of any real equation must have the same base units, or the equation is simply wrong. Quantities split into two families. A scalar has size only, mass, time, energy, temperature. A vector has size and direction, displacement, velocity, force, acceleration. The test is simple. Ask whether direction changes the answer. 5 kilograms is 5 kilograms whichever way you turn, but a force of 5 newtons left is the opposite of 5 newtons right. Vectors add tip to tail, not like ordinary numbers. Two forces at an angle combine into a single resultant, found by drawing them head to tail and closing the triangle. And the reverse is just as useful. Any vector can be split into perpendicular components, an across part and an up part, using cosine for the adjacent side and sine for the opposite. Splitting and recombining is the whole game. No instrument is perfect, so every reading carries an uncertainty. Two ideas are easy to confuse. Accuracy is how close you are to the true value. Precision is how tightly your repeats cluster together. You can be precise but wrong, a clustered set of dots, all landing far from the bullseye. Precise but not accurate. Errors come in two flavors. A random error scatters readings either side of the truth. You beat it by repeating and averaging. A systematic error shifts every reading the same way, like a zero error on a balance, and averaging never removes it. When quantities combine, add the uncertainties for a sum, and add the percentages for a product. Physicists love a rough estimate because it catches disasters. Before trusting a precise answer, ask, is it even the right size? Orders of magnitude, powers of 10, let you compare wildly different things on one scale, from the radius of an atom to the size of a galaxy. If your calculator says a person weighs 10,000 newtons, the order of magnitude alone screams that something is wrong. The method is to break a hard estimate into easy pieces you can guess, then multiply. How many breaths in a lifetime? Guess the breaths per minute, the minutes per day, the days per year, and the years in a life, then multiply. You will not get the exact figure, but you will land in the right ballpark, and that is often all a physicist needs. Here is the whole unit as one poster. Every quantity is a number and a unit, with all units built from 6 base units, and homogeneity lets you check any equation. Quantities are either scalars, size only, or vectors, which carry direction and add tip to tail. No measurement is perfect, so no accuracy versus precision, and random versus systematic error. And always sanity check with a rough order of magnitude estimate before you trust a precise-looking answer. And the boundary fence so you do not overvise. The detailed motion of objects, the forces that cause it, and the deep theory of waves all come in the units ahead. Here it is the toolkit every one of them depends on: units, vectors, uncertainty, and estimation. Get these right, and the rest of physics has a foundation to stand on.